your screen.
Okay, hello. Yes. Okay.
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 Yeah, we see a screen.
Okay. Okay, you can see. Yes.
So yeah, we see everything. Yeah, and our next and the last speaker for today and for the whole conference is Belliard with the talk Modified Algebraic Bethe Ansatz for XXZ chain on the segment. Please, you can start.
Okay, so thank you for the opportunity to speak here for this birthday conference. It's a pleasure. So I will present a part of work that I did recently with Nikita about the XXZ spin chain on the segment, and especially in the case where we don't have what is called U1 symmetry. And in that case, usual Bethe Ansatz techniques fails. And we should develop new approach modified Bethe Ansatz. So firstly, I just want to recall, at least for the last 10 years, me, I'm around this topic since a bit more, but basically I have the chance to work with Nikita in different topics, and there's a lot of progress was done in 10 years. In particular, the first collaboration was about a Scalar Product for Algebraic model, and there's few results that appear for SL3, and since there's more work that was done, a part also of things that Stanislas Pakuliak presents. So there's a lot of techniques that's about quantum groups and Algebraic Bethe Ansatz that appear in this paper, in particular the notion of multiple actions. That was very useful to understand the structure of a Scalar product. And then for me, I started this collaboration to talk about the modified Bethe Ansatz that I will discuss after. And later, we realized some conjecture, and Nikita joined me and other people to look about, again, a Scalar product. And what is nice, that's basically, we worked, I will not give details of this work here, but it's the XXZ case we will present, but the same idea are there. And basically, we realize how to this modification of Bethe Ansatz preserve a lot of structure and things that we already know from usual Bethe Ansatz, and we were able to make modification of result of Scalar product, what is called Isargin-Karepin formula, and also the Isargin determinant. That is something very important that appear in this correlation function that was already recovered, but it's this new context, so it extends a lot the result. And in particular, what is funny is that there's a totally new formulation of the same x66 Bethe problem in terms of this new modified Bethe Ansatz and the determinant. So all this story arrived to this very nice result that I will present in the case of XXZ to fix the Scalar product of Bethe states. In the case where one is on shell and the other is off shell. And it's just something connected to linear system and give a very simple proof. And in particular, it was able to prove the case of modified Bethe Ansatz that we don't just have some very hard combinatorial proof of that, but this is cover known case about the SL2 case. And we extend this to the XXZ spin chain with general boundary condition. That was the main model to motivate the question of modified Bethe Ansatz, and also other techniques I will mention, expression variable or orthogonal Bethe Ansatz. And we also continue to look what we can do mixing now states from the usual Bethe Ansatz and other modified Bethe vector. So there's work on that. So it was a lot of collaboration, fruitful collaboration on this subject. So let's now just go more on the problem of the model of XXZ with open boundary. So I will just quickly recall the important quantum integrability of the model we are looking for, and the role of Young-Baxter equation and reflection equation that give. And recall the content inverse scattering method for this boundary case that was done for the case that is called a diagonal case. So I will just in a type of boundary condition you consider in your chain, and explain how we can modify these techniques to find the general boundary case. And the difference is the presence or absence of some U1 symmetry. It's total spin, for example. And the main result in terms of its expression of the eigenstates and eigenvalue in terms of the Bethe parameter and the set of Bethe equation. And all this can also see as the off-shell action of the transfer matrix. And this is the key result that you should obtain before looking to correlation function. And in particular, from this algebraic result, we can start to look and construct the Slavnov formula using the linear algebra. So let's closely recall that the complementability, so I will be very short. From the knowledge of the Yang-Baxter equation, we can write many types of model. In particular, we are looking to diagonalize some part of the algebra that is the maximal Bethe algebra. It's called Bethe algebra, so the transfer matrix and all the other commuting quantity. And this can be done from algebraic Bethe Ansatz. Many things was done. So and Nikita, as it was mentioned in the talk before, is known for this this contribution about correlation function and asymptotic of this object. And also for the boundary case, so here you have a new equation, so you have a new object, K matrices that will allow to construct your spin chain. And you'll see also, here also there's a lot of result, but it seems that for many times in the paper of Klianin, there's mentioned, we know the generic boundary solution. So we know that there are the models that respect, from the algebraic point of view, all the constraints to be integrable, but Bethe Ansatz don't work. And basically, what was the point? So the point is, for the usual Bethe Ansatz, you can find what is called a reference state. And in terms of representation theory, it's just the reference state of Eigen-West representation. So for finite dimensional models, that's theorem from Tarasov and maybe after other people. So I learned from notes from Alexander Molev that say for JLN model, you always have Eigen-West representation. So for finite model, so this vector exists. And if you have U1 symmetry, it's this T of is this Eigen-West vector is eigenvector of the transfer matrix. But if you don't have the U1 symmetry, as I will show in terms of operator, you don't have anymore this condition. It's quite natural because, in fact, if you don't have U1 symmetry, the state should belong to all the possible total spin subspace. So the solution, all the space should belong more or less in some linear combination of elements of all the space. And so from this paper of Klianin and De Vega, and I don't remember all the guys that show the non-diagonal case solution. So people start to look about what we can do, and they impose constraints between the parameters. So you have some parameters that are in the model, and putting some constraints, they can restore some kind of new decomposition of the Hilbert space, and they can, by different version of the Bethe Ansatz, so analytical Bethe Ansatz, it's something you're just looking to eigenvalue, and you are using more or less some kind of fusion hierarchy constraint on the transfer matrix to fix and some analytical property you expect from the system, or from asymptotic analysis directly of the transfer matrix. You can have enough information to guess the form of Bethe equation. So, and to fix all these constraints, they have to fix constraint between parameters. So it was a study by Nepomniachtchi. And also after generalized from algebraic Bethe Ansatz, they understand how to modify the work of Klianin. So introducing, I will come back on this, some gauge transformation that come back Baxter work of XYZ, and later Badeyev, Taktajan work to diagonalize X-Y-Z model from Bethe Ansatz, and also the method. But finally, people develop alternatives, in particular, important separation of variable, because it's inside the separation of variable, there's also the construction of some kind of orthogonal basis in terms of the operator and the homogeneity, that it's very representation dependent, but is very important tools even for modified Bethe Ansatz to prove some part of the theorem. And what was the revolution in terms of thinking the Bethe equation and the eigenvalue? It was what is done by this Chinese group, Cao and collaborators, that add a new term on the eigenvalue and the Bethe equation, and this new term balance the problem and allow to fix all the asymptotic for this analytical version. So of diagonal Bethe Ansatz, it was just at the beginning the idea to add this new term to fulfill all the constraints that are in the same more or less with separation of variable, at least for finite model, because I always just speak about finite model here and analytical Bethe Ansatz. And this new term, and by the modified Bethe Ansatz, we understand the origin of this new term in terms of the operator and action of new operator to construct the Bethe vector. So the model, so as I say, so we are looking to the spin chain XXZ with boundary. So you have two boundary, the first and the last side, and you have coupling with some constant. And here you have the usual bulk structure. So this model, as you probably all know, can be constructed from constraint group structure. So you need R matrix and K matrix. So in that case, we choose that set of solution for this equation. And doing this, transfer matrix can be expressed in terms of some operator A, D, B, and C that act on the Hilbert space, and that was introduced in the paper of Scrianin, and that allow after to construct with this B, in particular in the diagonal case, we can construct Bethe vector by multiple action of this object, of this B, on a reference state. So basically, if you have just diagonal case, so you kill all this term, all the non-diagonal, it's well done. There's something that makes that, in fact, all the system, when you act with R matrices on the vacuum, you have upper triangular form. And so basically, all the construction of the K here, all this thing act on the usual vacuum, so all the spin up in triangular form. So directly you can see that the usual reference state work also. It means that for diagonal case, you have the same reference state for RTT relation or reflection equation. But if you don't, so if you consider just K minus here and you look to the representation of this object, there are techniques that was developed by Cao et al. So just before, so before making this transformation, so I will just show what is the new equation we are looking for in this modified Bethe Ansatz that will add the new term in the Bethe equation. So for that, the first model I consider is the case where you have lower upper triangular form. So in that case, you see you kill that term and that term. So K plus is triangular. When you act on the usual vector, all these matrices are triangular, so everything is triangular. You can use the user reference state as the reference state of the model, but you will have also this new term, this B here, in the transfer matrix that is new from what Scrianin have usually, just no non-diagonal element, so B or C. Scrianin just diagonalize that part, and all the constants are 0. So when you do that, so exactly, you have this first diagonal, and you have this new B operator. The highest weight is always like for scrianin. So you have Eigenspace representation, you have A and D operators that give some non-function, and C that annihilate the vacuum. And you can look for a Bethe vector just acting by many B's. And if you do that, so I do not here make details, but from the algebra, the reflection equation, you can extract commutation relation between the operator A, B, and D and B, and you can move ordering over acting on the T, you can move the operator and show that the off-shell action of the transfer matrix means that all the parameters we choose here in the B are free parameters, have this following form. So usually you don't have this first term. So in particular, si I took kappa to 0, we just have what is called wanted term with this factor here, lambda. That is some non-function, I do not specify here, but it's some non-function, usual eigenvalue. And unwanted term here with some function here that depend only of the parameters that enter in the vector. If we recur that such function at 0, it gives a set of Bethe equation. So on shell means that we consider this set for the parameter u equal, but this function equal to 0 for all the I. Doing that, we see that we just have these two terms, the first term. So if we don't have this term, it gives, okay, we have T gives some eigenvalue. But we should understand this new term. And it appears that this new term of the property, if we fill n of B, so depending of the type of representation, so the number of parameters, so it's something that in the usual Bethe ansatz depend of the sector of the total spin you are, so you can add different sector. Here you have a fixed number, and it should be enough to fill all the Hilbert space in terms of some kind of functional basis you can write in terms of the operator, having different parameter inside. So we don't go into detail for that, but how we can describe this just to check that in that vector with n, when we develop, we can show indeed that we have linear combination of 2 power n different elements. And you can count this element just by some property of the set of parameters. And doing that, what you see is that if I have n of, so this for n, it means that it's Bethe vector cover all h. So you have all the possible states inside. So if you act again, we imagine that, okay, we should have something if we want to add this new term that appear from in of diagonal Bethe ansatz, we should have some kind of relation like that. And so we look, and indeed we can prove that we have such relation with non-function. And this new term, adding this, will add just linear addition, the new term to the eigenvalue and to the Bethe equation. So that is this equation that algebraically explains the new term in the Bethe equation. Okay. Now, if we want to do the same thing for the generic case, so it just means that we drop here that constraint. First thing, here we don't have any more upper triangular form. So what I say that looking to the usual state here that make all the R triangular, here you have the problem because you have some matrix that is not in the group of triangular elements. So it means that this state is not anymore a good candidate to find some eigenspace representation for this algebra, this ABCD. And what can be done, and was done by this Chinese group, is to use what is called gauge vector. So this vector and covector appear, as I said, so in the paper of Baxter. So not exactly in that form because it was in the elliptic level, but they use this the same object, and it also appears in works of Jimbo and collaborator about phase vertex correspondence, and in fact this is mapping between phase vertex. And so this Chinese guy introduced this new operator that appears that corresponds to kind of family of I think it's dynamical reflection equation, but there's a lot of different type of class of algebra, but a link with dynamical reflection algebra. And doing this, after you can also use the same vector, the same object, to show that you will have highest waist representation. So basically with this this transformation, so you can transform your operator. So basically you see that are just linear combination of the 4 generators, so, but that depends on some additional parameters. So here we can see with the matrix that it's just linear combination. So you have a map to rewrite the T in terms of this new operator that depend on this parameter M. And after some algebra, you arrive to this formula, and you can rewrite the T in terms of a diagonal part. So it's some kind of, in terms of this new dynamical operator that depends on the M. So in fact, the M is arbitrary, but when after we have to fix the structure, we choose one. So this M, it's quite arbitrary. The T of U, of course, do not depend on this M. And doing that, you see 2 things. You see, okay, we have this 2 parameter is here in front of non-diagonal elements. So in particular, I mentioned that there's this result about constraint between the parameter and asking that these 2 coefficients are 0, and also that's is what I say just after, we want to have eigenweight representation, give exactly the set of constraints that was found by Nepomniachtchi and then refound by in that algebraic way by Caro and collaborator. And so doing this, you can find a choice of parameter. So you fix this alpha and beta that are 3 parameters that come from this gauge vector. So something that are free. So we can, for each choose of this alpha, we can define a new transformation from T to one basis or another. So I will say we will have 2 transformations, one to generate the operator that will act nicely on the eigenweight vector. So it's some kind of eigenweight vector because we have some shift properties that can appear, but we see that, okay, we have A, D, and C that have eigenweight property. So we can construct that by that transformation. But if we do that, we still have the problem, we have the B and C. So we can do a second type of transformation. That's what we call the modified transform matrix. It's just a transformation. We choose the parameter such that, in fact, we kill the B and C. So we are wanting a transformation. So as it's free, it contains the initial problem, but it just rewrote in a form that we have just 2 family of operator diagonal type. Modified because inside there are linear combination of a non-diagonal element of the monodromy, the monodromy matrix. And the point is, as all this is just linear system, we can express this A, DL, and DDL in terms of course of the A, DR, and D, and C, and D, etc. And then we can look to the action of the A, DL, and D, DL on the usual, on the reference state, in the case DR. So using this linear combination, we see that, okay, we don't have eigenweight representation, but what is very nice, that we still have the usual diagonal term, and we have something that generates a new modified creation operator B. And that is what we will call a modified creation operator. And this is after that we say, okay, let's fix. So here this is just more subtle in that model that for x66, you have to make shift in the product of operator, that is the dynamical character of this algebra. And you can then choose to construct the Bethe state in that form. So where we have chosen DL here. And doing that, after you make ordering, etc., and you see that, okay, I have a new term. So by ordering, you recover the diagonal term. Plus, there's very nice simplification of the terms that come from this additional contribution here, and everything just factorized on one term with a very simple factor here, and some non-coefficient here that is not wrote. But and after you can say, okay, this I should fix a number. I should look. So I look at what the dimension of my model. I compute, and I know the number of variables I need to have a complete basis and be able to describe all the spectrum and all the states. And this depends on the spin. So if we change, so this M here, it's if you have n spin 1/2, but in fact, the formula should be the sum of the SG over 2, or no, the sum of 2 SG, if you have different type of sites. So it will be similar formula. So, but this is representation dependent, and you can show that, okay, you have this structure in wanted and wanted terms that can add this new term in the off-shell action of the transfer matrix. So this one way of proving that, it's just showing by in the paper we prove that formula. We use the basis, one of the bases as was developed by a separation of variable group, and in particular the basis where this B is diagonal. So all this system became some functional system that is, you can see that indeed it's you have only one solution, and that fixes all the lambda and the E. Okay, so we arrive to the result. That is the first main result of the modified Bethe Ansatz. That's the off-shell action of the transfer matrix. And you recover the structure with diagonal terms. So diagonal term, you have just two terms I wrote here. So F are some function and product of function. The U bar, yes, I do not explain so much all the notation. The U bar is a set of parameter of n parameter. And here you have the Bethe equation. So, and all the other terms. So once we have this, after the next step, it should be to look about the scalar product of the states, and to do this, cool of time. We move to the techniques. That's the results that we did with Nikita and Rodrigo Pimenta. That was used the techniques we developed before to x66 model. So here we can reward, so I will not go into detail of the function, but just give the idea. So we have the action of t on the Bethe vector. On the right, you can do the same thing on the left. And we have all this function, etc., etc. So what's the idea of solving the linear system? It's a point, I don't know, maybe, so you see the point is we want to look to that object, that is scalar product. So to have this linear system, we put in the middle some transfer matrix with here, if we remove U bar, it means we take a set of n+1 variable and we remove the variable number k. We took that variable, we put in T, we insert in the middle, and we act on the left and the right. And action of the left and the right, we know from this. And moreover, we say that this left vector is unshelled, so that term is just 0 because that function we impose to be 0. So the two equations are satisfied. So doing this, we arrive to simply to a linear system that depends on all this set of functions. And after some Cauchy transformation, introduce some Cauchy determinant, we can transform this system and show that indeed this the rank of this system is at least n, and as the determinant is 0. And doing this, it means we should be able to find a solution using the Kramer linear solution, as that gives the structure of the solution. So in terms of the determinant, so there's some transformations that we have to reconsider, and we have some unknown function to fix. So this fixes the structure up to a function that we have to fix. So this G function. Okay, so to fix that, after it's model dependent, we should go more deeper and look in particular to the asymptotic of the two equations. So from one end, so we take the asymptotic of that part, and also we take the asymptotic of the Bethe vector. We should look to our look to the algebraic development of the B and take the dominant term, and we can see that up to that function here that remain to be compute, we can fix the coefficient and find the scalar product in that case. So we're taking the x66 limit. We will reverse a conjecture we did with Rodrigo Pimenta a few years before. Okay. So that was more or less, I was quite quick on this. So, but basically the idea of what the result obtained for the eigenvalue and the eigenvector. So the x66 and x6z case for open case was done. It remained to understand the x6z case on the circle with twisted boundary condition with non-diagonal. In that case, as a result from separation of variable, but it's still to write down the Bethe vector and to look in particular also, now we can try to compute also the Slavnov formula. So another question to look that I don't write here, but maybe to look if this linear system can help to recover at least a formula for form factor, and maybe it should help for this modified version to obtain something. And the other big question was about this additional term. So because having all this result is just, as I say, the first two states before a long work about looking to a correlation function and asymptotic, as was, for example, a question that was shown in the previous talk. But the thermodynamic, in that case, we have this homogeneous term. For the moment, it's not really clear how this term. See, but for the moment, I should say that what appears from numerics and the studies, it's in asymptotic for thermodynamical limit, more or less, we just neglect the inhomogeneous term, at least in some regime, but I didn't look myself in details. It was just few results on this from a Chinese group, but actually it's a project with my student to at least look the structure of the Bethe roots for the equation and look a bit what should be for the ground state or for excitation, the structure of the Bethe roots, because we know for the first model that it was the knowledge of the of the position of the Bethe roots that allowed to see that, okay, all the ground states on the real line, etc., and it helps to look to this integral equation. And that was the first project that should read. So there's also a thing that I do not mention, but I work with Pascal Bazeilhac to extend the work of Jimbo Miwa, because Jimbo and Miwa use vertex operator approach to find a directly result for the half this its existing chain of the half line with diagonal boundary. So we extend result for triangular, and we obtain also with Kojima result for correlator, it's a one-point function or something like that. And it should be a question maybe also to look using, it should be some mix of the vertex technique used for XYZ and to understand this transformation, but at the level of the vertex operator. So this I do not look since a long time, but there's a point where we can probably find also results that could be compared with what we should expect from this limit. And the other point important about this theoretical limit is the work that was done by Véronique Terras recently with a collaborator that remarked that even in the diagonal case, when you take theoretical limit, it seems that the two boundaries seems connected and have a memory of the presence of the truth. So this I should study, and this should be something that says that maybe this homogeneous term should have some importance somewhere. So that's the question for SL2, and for the point, it's for the moment, even for the simplest 666 case, it's not clear for SL3 what should be modified Bethe Ansatz. So there's interesting result, in particular Nikita and Lashek work on this SL3 case and connection with Skrianin B and C operator and separation variable, and this is Gromov work, and there's a lot of connection, in particular in Zetlin basis, and but it's not totally clear how to relate this this object with this modified Bethe Ansatz. So this is another open question, and more or less I say what I can say. So if you have question I can answer.
Thank you. Yeah, we don't have next talk, so please ask any questions.
Or not, it's not.
Okay, Samuel. So in the usual diagonal case, thermodynamic limit, I am speaking about thermodynamic limit. It strongly depends on the region of delta of anisotropy parameter.
Yeah.
So in this case, do you expect that thermodynamic limit also depends on delta? So let's say massive, massless phase.
Yeah, it should probably, yes. I don't know, but it's indeed something that we.
Well, I think that if there is a massive phase, then probably thermodynamic limit should be relatively simple calculation.
Yeah. Because well, you should have very strong boundary fields to constrain all the both. Okay. You should imagine. I don't know. I assume that at least, and even after, but for example, I don't know if there's move regarding to the bulk case or to something adding this new term, if it's something of a function of this delta, but also of the parameter.
Also on other parameters, of course.
I don't know, maybe.
Yeah, well, in the diagonal case, by the way, it strongly depends on magnetic field.
Yeah.
Of course, yes, this I understand. Okay.
Okay, nice.
Okay.
And happy birthday to you, of course. It's not today. Yes. Okay, so and all this will it's just live in YouTube, or it will remain all the video will remain in YouTube?
Yeah, sure.
Казалось бы, показывает говорящего на автомате.
Okay.